Imagine confirming blockchain transactions in 200 milliseconds. Not minutes, not seconds, milliseconds. Today, we are diving deep into Flashblocks, the technology that's making this possible on the Base blockchain. So without any ado, let's jump into it. Traditional layer 2s batch transactions every few seconds, creating a poor user experience. While users wait for confirmations, their transactions sit idle. This latency kills real-time applications. DeFi, gaming, payments, all of them suffers. Then enters Flashblocks. Flashblocks is a pre-confirmation streaming layer built by Flashbots that breaks traditional blocks into mini blocks every 200 milliseconds. Think of it like video streaming versus downloading. Instead of waiting for full 2 seconds for blocks, you get incremental updates. Here's the architecture on a high level. Flashblocks runs on top of Base's existing infrastructure using rollup boost. Every 200 milliseconds, a new flash block containing about 10% of regular blocks transactions is created and streamed to nodes. Now let's start with the cryptographic backbone of Flashblocks. Flashblocks uses Ethereum's modified Merkle-Patricia tree for state verification. Each flash block contains a state root, a cryptographic fingerprint of the entire layer 2 state at that moment. The magic happens through differential updates. The first flash block includes full block data. Subsequent ones only transmit changes. New transactions, state updates, all of them goes to the subsequent ones, whereas the first flash block contains the entire block's data. This streaming approach enables fast verification while minimizing bandwidth. Now let's look inside the secure heart of Flashblocks, the trusted execution environment. This hardware isolated enclave is where all the magic happens, completely sealed from external interference. Here, 4 critical components work together. The transaction pool receives incoming transactions. The priority sorter then organizes them by gas. Then the state execution engine processes these transactions by updating balances and running smart contracts. Finally, the cryptographic signer uses hardware protected keys to sign each flash block. Every 200 milliseconds, a signed flash block emerges from this secure pipeline. The system operates on a precise 200 millisecond heartbeat. Collect transactions, sort by gas, execute state changes, generate proofs, sign, and broadcast. This isn't sequential, it's highly optimized parallel processing. While one flash block broadcasts, the next is already being assembled. At the moment, multiple flash blocks are in different stages of the pipeline. This ensures consistent 200 millisecond delivery even under maximum load. Now, you may think, how does Flashblocks fit different size transactions fairly? This happens through progressive gas distribution. Each flash block gets a portion of total 14 million gas available in a complete block. Flash block 1 gets 1.4 million gas, which is 10% of the total. Flash block 2 gets 2.8 million accumulated. Flash block 3 gets 4.2 million, and so on. This ensures small transactions confirm instantly in the first flash block, while larger operations wait for blocks with sufficient capacity. Now for the network challenge. How do thousands of nodes stay perfectly synchronized with updates every 200 milliseconds? This happens through differential streaming over WebSockets. The first flash block sends complete data, perhaps let's say 100 kilobytes, but subsequent flash blocks only transmit what changed or if there are any updates, typically just 5 to 10 kilobytes. This differential approach, similar to video streaming codecs, dynamically reduces bandwidth requirements. The result? Every node on the network maintains identical state within 200 milliseconds. When Alice sends tokens to Bob, every node sees this change almost instantly. This isn't eventual consistency, it's near instant global consensus. After 2 seconds and 10 flash blocks, it's time for final assembly. This is where our streaming architecture becomes a permanent block record. All 10 flash blocks merge into one complete block. The system calculates the final Merkle root, the cryptographic proof encompassing all state changes. Every transaction from every flash block is now part of this unified structure. Now at this point, this is on layer 2. For example, base layer 2. The final step, submission to Ethereum layer 1. This provides ultimate finality and security inheritance. Flashblocks gave us speed through streaming, but Ethereum gives us permanence and decentralized security. Now let's understand how you can actually use Flashblocks using your QuickNode endpoint. To access Flashblocks, you do not need to do anything additional. If you already have a QuickNode Base RPC endpoint, you can just use that. If you do not have one, you can simply create one by going to your QuickNode dashboard and clicking on create endpoint and selecting base. So to access Flashblocks, you need to keep in mind a few things. It's just a pre-confirmation block. So any transaction you send via the QuickNode Base RPC endpoint goes to the Flashblocks. But if you need the Flashblocks data, for certain methods, you'll have to use the pending tag. For example, for get block by number, for get transaction count, for get balance, you'll have to use the pending tag. So to showcase this, I have a really simple script where we will be sending a transaction on the base Sepolia testnet and getting the statuses of that transaction. So this is a very basic script where we are just importing ethers, getting our RPC endpoint and private key. Never save your private key in your code. Then this is our main function, demonstrate Flashblocks transaction, where we have a console message to show that we are starting all the processes, and then we initialize the provider and wallet, and then we print the chain ID and the wallet address of our sender, and then also get the initial balance from our wallet address. Then we start to prepare our transaction. This will be our recipient address just for the demo purpose, and we will send 0.001 ETH to the recipient. Then we will get the recipient's initial balance and print that in console, and we will get the fee data. We'll get the gas price and print that as well. And over here we are constructing the transaction structure, or you can say transaction body, and finally sending the transaction over here and printing the transaction hash in the console. Then after this particular point, we will start to actually monitor Flashblocks data. For example, for sender and receiver balances, we will get the balances along with the pending tag, which we saw over here in the documentation. To get the balance, we will have to use the pending tag if we want to get the balance for the addresses of Flashblocks. Then we will print individual balances for both sender and receiver. And then there is this flash block counter which we have, and a start time, because we have this where we will get the block with pending tag again because we want to get the flash block. Then we also get the pending nonce in case we want to send multiple transactions. This can be helpful. And if you want to send multiple transaction, getting the pending nonce and then getting the pending balances for each of the party, sender and receiver over here, can be helpful. But in this case, it's just one transaction, so we do not have to worry about that. And then we are waiting for the transaction confirmation. Then we are just calculating the confirmation time since the transaction was sent, and then printing all the details like confirmed in how much time, the block it was included in, gas used, and the status of the transaction. Then we get the senders and receivers final balance and print them. Then finally we run our function. Now to run this, we will need to replace this with the actual private key and this with a QuickNode Base Sepolia RPC endpoint. So let me go back to my QuickNode dashboard, then copy this HTTPS URL, set it over here, and let me also get the private key and then run the code. Now to run the code, let's just do node index. Right, you can see that we are getting the updates for each flash block. So let's understand this step by step. So we initialize the provider, got the chain ID, got the wallet address, got the initial balance of the sender, then prepare the transaction, got recipient's initial address, got the gas price, and then send the transaction. This was our transactions hash. Then we monitor with Flashblocks. So these were the balances for sender and receiver. and you can see the receiver's balance has already been updated because it was included in Flashblocks. Then we wait for confirmation until it gets added to an actual base block. So you can see transaction in pending block, Flashblock true, transaction in pending block, then Flashblock 3 again still transaction is in pending block, then Flashblock 4 still pending block. So this keeps on happening until we reach Flashblock 8, and then after that it finally gets added to a actual base block, which is block number 29336838. If we take this transaction hash, go to base scan and go to base Sepolia testnet on base scan and look at the transaction, you'll see that it was indeed added in 29336838, which was the block number we got over here. But we were able to see that the balance of each sender and receiver was already updated in the flash block, which you can see over here, which we were able to get via our QuickNode endpoint from the base node, and we were monitoring each and every flash block until all of them got added, or until our transaction got added into a actual base block. So this is how you can send your Flashblock transaction and monitor your Flashblock transaction. So hope you learned a lot of things about Flashblocks in this video. If you did, give it a thumbs up, subscribe to the QuickNode YouTube channel, and I'll see you in the next one. Bye bye.